Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to talk about position, velocity, acceleration, and acceleration, and how they're related graphically. So it's very important when studying motion to know what all of these things are, and the graphical relationships between them are just essential. All right, so let's start with position. So the position of an object tells, basically, just like its name implies, tells where it's at. Usually in physics, we use a set of coordinates to do that, maybe x and y, or in a one-dimensional problem, maybe just x. So in this example here, this x, this is representing the position of some particle with respect to some coordinate system. Right. Then velocity. Now remember, velocity is rate that position changes, and as far as how it's calculated, it's equal to change in position over change in time. So in a one-dimensional example, that'd be delta x over delta t. All right, calculated this way, you're getting what's called the average velocity. I'm going to go ahead and put a bar over this to indicate that that's an average. Important thing to know that on a position graph, delta x is a rise. And if t is on the horizontal axis, then delta t is a run, and that makes delta x over delta t equal to slope. Slope of your position graph. Now, let's talk about acceleration. Acceleration is the rate that velocity changes. Therefore, mathematically, it's equal to change in velocity over change in time. Anything calculated with these deltas, these changes, these are averages. So I normally put a bar over this to indicate that, that in that calculation, that's an average acceleration. Now, on a velocity graph, delta v is a rise. It's a vertical displacement on a velocity graph, and delta t is a run. So this is equal to slope of velocity, or a velocity graph. All right, so what I'd like to do here is go through an example. I'm going to draw a velocity graph, and then from that, we want to be able to sketch the position graph and the acceleration graph. So I'm going to go ahead and do that here. So I'm just going to make up a graph here. All right. And what I'm going to do is save this right here. I'll go ahead. All right, and what we want to be able to do now is from this velocity graph, we want to be able to sketch a position graph and an acceleration graph. Now, important thing to realize, at t equals 0, we're here on the graph. So whatever particle this graph is representing, it started from rest. As time goes on, the velocity is getting a little bigger, a little bigger, a little bigger, a little bigger. So out to this time, whatever this is here, I'll just put t prime here for now. The velocity is increasing, so this thing was accelerating. Now, accelerations rate that velocity changes. It's delta v over delta t. So in this time frame, this particle was accelerating. Right? The dead giveaway is the fact that the velocity is changing. Now, also notice that this is approximately linear. Maybe not perfectly linear, but it's pretty darn close to straight. I could pick any two of these points on this line and calculate a slope, and I'm going to get about the same value. So the acceleration is basically constant in that region, and that slope is positive. So our acceleration graph out to this time might look something like this. Right, whatever this value is, it's equal to the slope of this line. Now, I'm not going to go through any numbers in this example. This example is just meant to be conceptual. Let's go ahead and continue talking about acceleration here, and then we'll talk about position. At this point right here, the velocity is not changing now. This distance is about the same as this distance, same as this distance, same as this distance on this graph. So now the velocity is constant, the slope is 0, the acceleration is 0. So on my acceleration graph, this drops down here, and then is 0. Now we're going to talk about position. So going back to this 0 to t prime time frame, remember when your velocity is constant, that would mean the slope of this position graph is constant, and that would make this graph linear, right, if your velocity is constant. However, this velocity is not constant. It's increasing, which means the slope of this graph has to be increasing. That means this graph has a property called concavity. And if the slope is increasing, it means it looks something like this. It's important to realize when I talk about slope increasing what I'm talking about. Right? So let me draw some tangent lines. So I'll draw one right here. So your velocity is the slope of the tangent line. If I drew a tangent line right at that point, it might look something like this. And then as time goes on and we move along the curve, whoops, now the tangent line has a slope maybe like this, except I probably got a little close there, or maybe something like this. And again, if I go a little bit further along this curve, now the tangent line has a slope that looks maybe something like that. So again, this increasing velocity means on our position graph, as I move along the curve, the slope has to get steeper and steeper and steeper. And that's why it's got this concavity property. In this case, this graph is concave up. So out to t prime, our position graph would have an increasing slope, maybe to something about like this. From t prime on, now the velocity is constant, which means our slope is constant. So the rest of this graph is linear. And I'll just put an arrow here indicating that this keeps going. I don't have enough room to draw it all the way out here. So again, important points of this conceptual example. Before this time, t prime, whatever it is, our velocity is changing. So we are accelerating, and the slope is not changing, so that acceleration is constant. So if I were to sketch an acceleration graph, it might look something like this. Our position graph would have to have some curvature to it. It'd have to be concave up because our increasing velocity means the tangent lines have to be increasing in slope, right, out to t prime. From t prime to the right, our velocity is now constant, which means our acceleration is 0, and our position function is now linear from there on out. So again, this was just an example. This example is just meant to conceptually talk about the relationship between position, velocity, acceleration. It's important to conceptually understand how these graphs are related before we can attach some mathematics to these graphs and use them to solve problems. So hope that this video helped go over these concepts. Have a great day.